Thank you so much for the warm welcome and welcome to this session. In comparison with the awesome presentation of David, I think my presentation is going to be very boring for you guys. Especially, I'm going to touch the topics which are machine learning, analytics, which are math and statistics oriented. So the quotient of boredom will be a bit higher, but I'll try to pacify it as much as possible. Let me first start off by acknowledging the organizers that they gave me the opportunity to come here and present before you guys. And I do hope that next 30 to 40 minutes will be interesting, insightful, and enlightening for all of you guys. What you see before you is a topic, that's the first thing, but actually there are three main keywords that are quite prominent in this particular title. First is scalable, analytics, and cloud. Scalable, which relates to scalability, that we'll explore as well. Analytics, which relates to intelligence, machine learning, these are similar words. And cloud is something that's quite obvious. All of these phenomena, concepts, technologies, whatever you want to call them, they are there, they are in the business, they are being used by organizations, enterprises, and all of them in their own individuality are adding a lot of value. So companies currently are using scalable platforms. Companies are doing analytics, and companies are using cloud for a number of purposes. But what I'm trying to, and I will try to convey as a part of this presentation, that yes, all of these entities exist in isolation, but the true value of whatever you want to do actually is unleashed when you use all of these entities or concepts or technologies in conjunction. And I'll try to highlight that when you do, for instance, analytics in isolation, and when you combine it with some scalable platform, and ultimately when you integrate it with cloud, what value you get out of it, which was previously not present. So that's going to be our journey for today. And a little bit about me. I'm currently working as a senior consultant in Deloitte. There's an upcoming training of data science happening in Deloitte as well, which is going to be very hardcore on data science and machine learning. I'm going to be one of the trainers. I recently presented at DataWorks Summit, which is actually organized by Hortonworks in Sydney last year. I'm a premium Udemy instructor as well with around 17,000 students. I have launched 2 courses. There are many coming up as well. And if you want a coupon for that, that will be my giveaway for today. And I am a technical reviewer of an upcoming book on Hadoop as well, which is going to be launched in a couple of months. So enough of the bragging rights. Now coming to the main part, which is the agenda. So as I mentioned, that the 3 phenomena that we saw at a very high level, that is scalability, analytics, and cloud, we have a view in isolation, and we will gradually tread towards conjunction or integration. And then there will be a demo and a takeaway, and that's going to be our experience today. So as I mentioned before, that all of these innovations, if you, for instance, refer to Gartner or Forrester or any of the blogs or any of the market analysts out there, you will find these 3 keywords to be popping around, and these are the drivers of innovation. They are disrupting industries in so many ways. So we all understand these things. These are all the cliches or the buzzwords that we hear. But I want to go further, and I want to understand that if you expedite on intelligence, and if you are doing it in isolation again, that I'll explain a bit more, what are the challenges and still what are the opportunities still there? And I'll slowly pivot towards scalability as well. So intelligence is a very vague word. I mean, intelligence can be like, if you are intelligent, that's good. But in the context of doing something with the data, what it actually means is that if you have a lot of data, like you have CRM data, you have social analytics, you have sensors data, you have web data, and so much data is out there, and we are living in the world of big data and all of that stuff. But if you have that data out there, and if you are able to use that data to somehow process it and mine it and drive some patterns out of it, and ultimately, if it is used to support your business decision making, that's where the true mantra of intelligence lies. So if you have data, you mine it in somehow, and then you drive some insights out of it, and if those insights help you in your decision making, and if those decisions ultimately help you in some of your KPIs like churn prediction or fraud detection, that's where the true value of intelligence lies. So that's the first point of intelligence, which is the value. And there are so many use cases like that I mentioned as well, like churn prediction. If you want to predict which of your customers are going to be churned, if you want to predict whether this particular customer who's applying for a loan is the right customer or not, or will he be someone who will not pay your loan back. if you want to tailor your marketing according to the customers, that if there are certain customers who are more pivoted towards online channels, if you want to treat them differently, or if you have a more of an in-store guy and you want to provide the marketing a bit differently. So these are all the use cases that are out there being used, being leveraged, and a lot of value is still being realized. So that's one aspect of it. In going further under the hood, because machine learning and intelligence, it's important for all of us to understand what actually happens under the hood, is that, and a very quick overview is that its pipeline looks something like this. Like, you acquire data, you do some sort of transformations on top of it, you do some exploratory analytics, you then develop model, you do prediction, and then you do some basic evaluation. So this is a very high level overview of what you actually do in machine learning, and using these steps at a very high level, you are able to drive some intelligence out of it, and you ultimately get some insights that help you in your business decision making. So that's the context of intelligence. Now, what was the traditional approach? Now, machine learning is not a new domain, and many of the domains like artificial intelligence has been in industry, not in industry, has been around since 1980s. So the traditional approach was that if you have data and if you want to analyze that, if you want to apply some machine learning, if you want to apply some intelligence, then you use those tools or technologies or those languages or frameworks which only worked or used to work in single node. So if you have a server, you use R or Python, I'll highlight that as well, and you want to analyze data, that data has to fit in the memory or the processing capability of the server where you are running your analytical tools. So that's the first aspect of the traditional approaches. And the other aspect is that all of the data used to be fit in memory as well. It's not like if there is data and if the memory, it cannot be fit in memory, you cannot process it. These are the challenges that were there, and there are smart ways to go about it, but still these are typically the challenges of these typical tools and technologies. So R, Python, and within Python we have a lot of amazing libraries like scikit-learn, pandas, numpy. In Java we have Weka, and the list goes on and on and on. So over the years, people used to use, and they're still using these tools and technologies, and if you want to employ these technologies and tools in isolation in an environment which is not scalable and an environment which is not elastic, the challenges are something like these. So firstly, I'll highlight the opportunities or the pros, and then I'll highlight the cons. So first thing is, if you want to use these tools, if you are working in an environment which is non-scalable, you are not in all like dreadful condition, there are still a lot of good opportunities or good aspects of it. First thing is that coverage. If you want to use some advanced algorithms like neural networks or some advanced XGBoost or something like these tools and technologies are really excellent on that aspect. If you use R, there are amazing libraries out there. Similarly, it's the case of Python, scikit-learn. So much coverage of algorithms are there, and these are the challenges that you will see in the analytical and the scalable platforms. And second is that if you use these, visualization is one of the most important aspect of machine learning pipelines. You grab your data, you do some exploratory analytics using visualization, and you try to drive some patterns out of it. If you use these tools, tools like matplotlib, in Python it's super good, in R we have ggplot, super good, and also the third part of mutability is there as well. By mutability, it means that the luxury of changing your data in memory. And this is the problem that becomes quite crucial when you work in a distributed environment, that is in that scalable environment. So these are the good things. If you use these tools, these are the luxuries that you have. You can use a lot of state-of-the-art algorithms, and which are complemented by strong visualization, and you can leverage the mutability to do your machine learning pipeline in a very good way. But the challenges are, again, you're constrained. That is, if you are using R in a server, yes, the data has to fit in memory. And the second aspect is also in the context of scalability is the compromise that happens in data locality. Now, one of the reasons that big data evolved so much and added a lot of value compared to traditional paradigms of computing is that the basic notion of Hadoop or distributed computations frameworks currently is that processing has to happen where data resides. So if your data is residing somewhere, and if you want to bring all of your data over some place and you want to do something with it, that violates the principle of data locality. And Hadoop and Spark, they leverage this concept a lot to do a lot of optimization. So if you use these tools, unfortunately, you compromise with the data locality because a lot of network traffic happens. And another thing is that ultimately the nature of the data scientist is that they do some sort of experiments. It's very iterative in nature. They explore, they develop some models, they get back the data again, they again develop some models and all of that. And ultimately what you develop has to be productionized somewhere ultimately in your business as well. So ultimately what your prototype, your proof of concept has to be sustainable, has to be efficient, robust in terms of performance. It should have all the non-functional capabilities. So that's where the challenge happens. That if you use these tools and if you expect these tools to work on, number one, data sets that are big enough for them, that's where the challenge occurs. And also this challenge is more crucial when you use tools like R. So that's where Python is a bit good, because typically data scientists use Python for prototyping and ultimately pivot to Python. Data scientists use R for pivoting, prototyping, and they ultimately pivot to Python for making their prototypes and proof of concepts more sustainable. So that's an overview if you use intelligence in isolation and using the tools that are listed there. But the solution is scalability the ultimate solution to some of the challenges that I've highlighted there? Seems to be, but let's see what happens. So scalability at a very high level, what it basically means is that if you have data sets and if your data sets are growing and growing, then there are two approaches to handle that problem. One way to address is that you make your servers bigger in a vertical way, like you make your servers RAM more beefier, you make your servers have more compute power and all those. So you are basically making your box, your node, your machine bigger, but you are not basically forming multiple nodes clusters. You are making your machines bigger. That's one way, and that's the way that typically previous traditional technologies like Teradata and SQL Server used to leverage a lot, and then they pivoted to MPP as well. The second approach is something called as horizontal scalability, which means that if you want to address big data problem which cannot be processed in one node, then instead of making that node bigger, rather expand or branch out in a horizontal fashion. That is, add more nodes to your environment and allow to leverage your environment in such a way that computation happens in parallel in all of those nodes. So that's the premise behind current big data or scalable platforms. Hadoop is built on this basic premise, and it offered a lot of other capabilities like fault tolerance and all of those things. So that's the basic premise, that if you have a big data problem, scale out or perform horizontal scalability. From value point of view, there are a number of use cases of big data. If we explore it in isolation, it's being used for ETL data offloading as well, ETL processing as well, and that's one of the use cases. I'm currently working in one of the Australia's biggest telecom company. So their use case is that their data warehousing but the technology or the tool is like not performing, and they want to pivot to big data for their processing requirements. In addition to that, there are a number of other big data use cases as well, from IoT to stream processing to name a few. So it's adding value a lot. And analytics is actually one of the subsets of the use cases of big data, if you can think of it. Now, again, coming to the life cycle of it. So the typical life cycle looks something like this, that if you have a big data problem, instead of scaling up, you scale out and you provision VMs, you do some inter-networking with them, you configure operating system, you provision Hadoop, for instance, on it, and then you ingest data on that cluster, do some processing, then ultimately you either persist it or do something else with it. And here you have multiple options. One of the options is the EMR that David mentioned, and there are other flavors or vendors of Hadoop available as well, like Cloudera or Hortonworks or MapR, to name a few. And that's where the difference happens. You can use vanilla Hadoop as well. You can download Hadoop binary from internet and configure, but if you use, for instance, Cloudera, it really takes away the pain to actually manage your cluster and to install a number of tools that come with Hadoop ecosystem. Now, tying it back to the analytics, there is a complete taxonomy of scalable analytics as well. So taxonomy is a heavy word, but what it actually means is that on such platforms, you can do analytics in a number of ways. And you will see some, and I will try to highlight a couple of interesting patterns or trends in that aspect as well. So when I ask that Hadoop, what thing comes into your mind? Is it Hadoop like one tool or technology, or is it like a suite of tools that work in conjunction, or is it like name of an elephant? What is it? What actually comes into your mind?
Big data processing.
Yes, but if you go one level down, then from software point of view or from tool set point of view, what actually it is? Multiple tools, parallel processing that allow you to do parallel processing. So Hadoop, the term used is like an ecosystem. It's basically a growing tool set that do different types of things. There are tools that do processing. There are tools that do storage that add storage capability. There are tools that manage metadata. There are tools for authorization, authentication. So it's a complete framework. That's why it's being adopted very quickly in enterprises as well. Now, coming to that part, within that Hadoop ecosystem, what I've seen is that there are a number of tools that are coming up, like Apache Spark, Flink, Ignite, that are offering analytics capability on top of them. So for instance, if you use Apache Spark, it can be used in a number of ways for a number of use cases, that's fine. But if you want to use analytics, instead of resorting to another library like scikit-learn or anything else, anyways, Spark itself offers machine learning library as well. So the challenge is, so that's where a lot of things streamlined as well, and that we'll see in a while. And similarly, if you use Apache Flink, it offers machine learning library as well, and Apache Ignite is also offering machine learning library. And this is a trend that's happening, that you have one tool, for instance Apache Spark, that does batch processing, stream processing, machine learning, graph analytics, just to name a few. So that's one trend out of it. And if you want to leverage scalable platforms, use Apache Spark for instance, use its library and do your analytical use cases. There is another set of analytical capabilities on such platform, and these are libraries like H2O.ai and DL4j for deep learning specifically. So you can use these libraries, and they have very strong integration with Spark to do your analytics at scale. And H2O.ai specifically is considered as one of the leaders as per the Gartner quadrants of 2018. So it's really powerful, and it has strong integration with Spark. You can create H2O context and do a lot of cool stuff. Another dimension to analytical capabilities on top of scalable platforms is that what the trend that's happening is that a lot of integration efforts are being done to make traditional tools like R to work with Spark as well. So that's where you see tools like Sparkly R that allow you to use R and offload the computation to Spark. If you ask me, is it mature? I will say it's not truly mature, but it's something that's gaining a lot of traction. And those people who are good at R, and if they have certain tasks, they can use Sparkly R to do computation in Spark. So it's a good thing. And the fourth capability, again, the options point of view, is that you can leverage AWS or Azure as they offer machine learning libraries as well. And you can interact with them through APIs. Analytics and processing happens in the cloud, and you get the results back. So there are a number of ways to go about it. Coming to pros and cons. So we saw analytics, we saw scalable platforms. Combination of these still enable and have a lot of challenges as well. So the first thing is that pros, scalable. Does it relate to better intelligence? That's something that I'll highlight as a proof in the next slide as well. But generally speaking, if you have more data, your machine learning algorithms tend to become more accurate. So that's you can say a rule of thumb. There are some exceptions, but yes. So if you are learning, and if you have, for instance, 10 examples to learn from, and if you have millions of examples to learn from, that's where the difference happens. That's where quotations like practice makes a man perfect, those comes into play, and those intuitively hold true for these aspects as well. Streamlined architecture, you have, for instance, if you are using Apache Spark, you can use that for batch, streaming, and also for analytical use cases. And so that's where you don't have to toggle around between multiple technologies to achieve your objective. So that streamlines things a lot. And that also relates to lesser engineering to make your prototypes production ready as well. So if you have developed something in Spark, then little to no change is required to actually make your code production ready. And that also translates to companies' overhead to find good developers, and as well because things are really less complex. And again, the data locality is optimized. That's the crux of Hadoop. Computation happens where data is, so that's where it's really good. but still there are some challenges as well. It's not like all good, there are some challenges, and one of the challenges is the limited coverage of algorithms. So if you use, for instance, Spark, and if you use Spark ML or MLlib, you will find that there are a lot of limitations of the algorithms there, and even within the algorithms, if you do some advanced machine learning, you will find that there are a lot of limitations there. So that's one thing. If you have some state-of-the-art problem, and probability is that such algorithm or approach is not available in, let's say, Spark out of the box, you may have some challenges. You can resort to H2.ai or other tools to address your problems. Visualization. The challenge with visualization is that another example, so Spark out of the box provides you the capability to, who is currently aware of something known as histogram or discretization or these things, histograms. So if you have a data, you split it into certain buckets. So if you want to do such things, it's pretty easy to do in Spark. You have a big data set, you call, if you have a data in specific form, you call .histogram function and you specify I want to discretize or bucketize my data into 10 buckets, and it does the work for you, and it does in a parallel way at the worker nodes. It's not like a one machine process. But if you want to do something else, like you want to do scatter plots of 2 columns, or you want to do something else, then that's where the challenge happens. Either you bring your data back to where you are using visualization library, or you do sampling. So still the challenges are there. And the last thing basically is that as of now, who is aware of like trends like deep learning and neural networks and XYZ, right? So those people who are aware of those may appreciate the fact that they rely extensively on GPUs because they provide a lot of cores and they ultimately enable faster computation. The challenge with scalable platforms as of now is that, and specifically talking about Yarn, that it does not who currently knows Yarn as of now? I don't want to be so technical, so who knows Yarn? So Yarn is like a resource scheduler. So so that's the challenge with this presentation, because there are so many heavy concepts and the time is less, so that's why I will try to make things simpler. So Yarn is like a resource scheduler. If you have a cluster of 10 machines, it manages, okay, this job will get that many resources like machine or processor, and this machine or this job will get that much resources. So as of now, it can take care of memory and compute, but cannot take care of GPUs. So that's where currently the work is happening, and maybe in the upcoming versions of Yarn, it will be able to leverage the scheduling or the allocation of GPU resources as well, and that's where truly the value of deep learning will be capitalized, but still you can leverage scalable platforms for such use cases. Now, if again slowly moving towards cloud, so if you have a big data problem, you want to do some cool analytics, yes, and from pipeline point of view, the first point is infrastructure provisioning. So you have to provision a cluster of machines from where you install or provision Hadoop and do some cool stuff on it. That's fine. So that's where concept or phenomena of cloud tries to add its value. So there are 2 ways. If you want to provision Hadoop, yes, buy machines, buy servers, do networking by yourself, and take care of all the maintenance overheads by yourself. And once you are done with Hadoop, what will you do with those machines? And there is a time to provision those machines as well, and all of those challenges are there. And that actually adds your time to value. So if I'm a data scientist, and if I have a big data set, and if I want to use Spark to develop some machine learning model to do some prediction, and if I have to provision infrastructure by myself, or my business or my enterprise needs to provision by themselves, then it's going to take a couple of months, and the value of that particular model will be of not much worth. So that's the first aspect of it. So that's where time to value comes into play, and can cloud be a solution for that? Probably, we'll see. Now, this is a little bit of a digression from what we are currently discussing, but it's a very famous quote that it's not who has the best algorithm that wins, but it's who has the most data. So it's a graph that is basically showing that if you have lesser number of, consider it as your data or training set, if you increase your data volume or data size, then accuracy of your different types of algorithm tend to increase. So even very poor algorithms like memory based or let's say perceptron, for instance, they are very less performant or very less accurate at lesser data, but when you add more data to it, they tend to become more accurate. Now, I won't say that this is the rule of thumb, and I will still disagree with this statement in a context, but that will become a bit technical, because if this holds true for high variance models, but for high bias models, this may or may not be true. But still, as a rule of thumb, if you do analytics on larger volumes of data, you tend to develop your models which are more accurate, and ultimately which will provision more value to your businesses. Elasticity, a simple concept which basically means that if you want to do something, if you want to store data or do some processing, you can scale out or scale back very quickly. So that's one of the most compelling propositions of cloud environments like AWS. If you want to use AWS or Azure, what you can do is that you can spin up the VMs very quickly, and you can bring them down. So when you couple that with the previous things like analytics, and if you have a big data platform on top of it, time to value is truly rapid. So if you have a big data use case, you want to do analytics, spin up Azure VMs, spin up some some Hadoop cluster like Cloudera or something else, and deliver whatever you want to do. And that's where some other interesting patterns are happening as well. So I'm referring to Cloudera a lot, but don't take me for another way that I'm like their salesperson or anything. But there is an interesting product of Cloudera named as Cloudera Atlas. Is it Atlas or Altus, Madhi? Atlas. Altus. You are the Cloudera guy, but so that's where it also takes away a lot of challenges as well. So the main concept of Altus is that if you have let's say a Spark job or a MapReduce job or something else, this Altus tool takes care of all the infrastructure provisioning and everything. It runs a job for you in AWS or Azure and returns the results back to you. So that also signifies this particular concept that that's where the trend is happening as well. And it is truly fit for scalable analytics use cases as well. So if you have developed a model, a regression model, or any other model, and it is capable to compute, let's say, 1 terabyte of data, and if you have 10 terabytes of data, you can easily and quickly scale out in cloud. That's one of the good values of cloud. And the feature that you can pay and scale as you go, it's truly inviting and attractive for a lot of businesses as well, because there is less upfront cost, capex is lower, so it's all good. And it's good for transient loads as well. As David mentioned, that EMR is one of the main use cases of EMR is that you spin up the cluster, you do whatever you want to do, and then you bring them down. If you don't do that in a cloud environment, then if you have machines in place, you have to either use them or they are there and they become an asset, they become a liability for you. Now comes the demo part. Now I'm going to present a demo which is going to be a true big data use case, and I will explain why. And the key takeaway of the demo is that if you have a data set that you cannot process in a machine, and if you analyze that data in a big data cluster using one of the tools that are provided by these scalable platforms, you can do scalable analytics on the cloud very easily. So coming to the demo part, so I have a data set which is currently of 17.4 gigabit of size, and my poor system currently has merely 22 GB of space left in it. Not coming up? Oh. It's, I think I should duplicate my screen. Okay, sorry, I'll repeat. So I have a data set, for instance, and if, come on, which is 17.4 gigabit in size, not that big of a number, but still, for me, it's a big data problem because my system only has 22 GB left. So I'm at challenge because I want to analyze this data, and I cannot compromise my system and put 17 GB of data on it and lose all of interesting Game of Thrones series on it. So that thing is more valuable for me. It's valuable as well, but that thing is more valuable. So the challenge is I have this data, and here is a file system overview of that data. These are the files that you can see, and the sum of these files, each file is around 450 MB or so, and this file, all of these files equate to around this much gigabit of data size. Now what you are seeing before you is actually a tool that you can provision on top of let's say a scalable platform like Hadoop, which is Anaconda, and with Anaconda you get a notebook environment which is called as Jupyter that allows you to write code and get data that get output in line out of it. So this screen is big data before you because this is not my system, it is actually connected to one of the clusters that in Amazon Web Services, and I'm just using one of the tools that's installed on that cluster to do some things on it. So currently the cluster that I have is not much big of a cluster, but still, so it's a 3-node cluster. It's a small cluster, 3 nodes. Even one of the nodes is a master node, the other 2 nodes are the worker nodes, and this is when it comes to Hadoop, as I mentioned before, there are a lot of vendors. This is Cloudera's distribution of Hadoop installed on AWS VMs that are currently running. So I have a cluster, and this cluster consists of 3 nodes, and I have a data set of 20 GB in size, which I unfortunately cannot process in my own laptop. So I'll pivot to a scalable platform that is consisting of 3 VMs on AWS, which is a cloud, to do some analytics, hence scalable analytics on the cloud. So let's just see what we can do with it. So that's again is the file system view of it, and if I, for instance, if you skip the coding part, so this is the first, so if I have this data set, one of the first questions that I want to answer is that, okay, this is the data set, and how many records are there? Now that's the first question that anyone would definitely be curious to know. So there are around 800 million or so rows in this data set of 18 GB of size. So that's the first answer, or small, very humble analytic that I did to drive some value out of the data that I cannot process. And the second question is that if I want to peek inside the data, what my data looks like. So it consists of 3 columns. There are some dummy columns in it, and I've labeled it as a price, and there is a city column as well. So I can get a schema view of my data that's 3 columns. This one is ID column. This represents some price, and there is a third column which represents some cities of Australia as well. And from schema point of view, if I want to become a bit more geeky, then these are the data types of this data set that's currently there. Now I'm currently using Spark to do all of these things. So I'm using Spark, and I use Spark to load the data set, to do some sort of count, to print the schema out of it. So it's like I'm using one of the tools that is Spark, and I'm using this web UI or notebook, and ultimately doing these computations like count and XYZ that's happening in the cluster that consists of 2 or 3 machines. So it's like analytics, very, very, very basic. Now, one of the and I won't become quite crazy in learning some machine learning algorithms there. I've kept it very simple. So one of the first things as data scientists or machine learning engineers do is that they want to develop as much understanding of the data as they can, which is called as exploratory analytics. And within exploratory analytics, one of the questions that you want to understand is like, what are the basic statistics of my data? Like, what is the mean, average, mean also known as average, what is min, minimum value, maximum value, and all of these typical statistics as well. So using Spark, you can do it pretty easily. You can just call describe function, specifically on the price column, and you can try some insights that yes, I have a data set which has 800 million rows, mean is this, standard deviation is this, minimum value is this, and maximum value is this. If I want to do the same thing on my laptop, firstly I have challenges in terms of storing this data. Secondly is the laptop's memory is around 8 GB or so. I cannot like use those tools in a naive way to process this data and drive these basic statistics out of it. So I think that using Spark, analytics tools, its analytical capabilities, and cloud in conjunction with scalable platforms, I'm able to do some very basic statistics, and you can build on top of it. You can do some crazy machine learning algorithms on top of it and do some whatever you want to do. So that's a very basic demo of one thing. Now coming to the key takeaways. So my view is that, and I may be wrong, and you can agree to disagree, but if you have a non-big data problem, or you want to do some rapid prototyping, if it was me, I will always stick to R or Python or those traditional tools that I mentioned, because they give me really good coverage, because they allow me to do visualizations in a very efficient way, and they have mutability as well, and the community is growing as well. So I'll probably stick to that, and I'll advise the same for you. Now, if you want to go away from that path and want to go the other path, then actually the true value of performing analytics at scale, in my view, lies when you combine cloud, analytics, and scalability together to do some analytics. And I've written the term write data with it, which is crucially important. It's not like if you have terabytes or petabytes of data, and if it's garbage, and if you expect that, oh, I trained a model on 1 GB size and it gave me X accuracy, and I am training a model on petabyte scale and it will give me better accuracy or 2 times accuracy. It will not always be the case unless you have the right data in place. So that's where terms like feature engineering come into play. So focus on the right data. There is a probability that if you have huge data, but out of that huge data, your right data value size is not that big enough. So you have to think in that way. And the conjunction of these three still has enabled a lot of opportunities for sure, but there are still a lot of challenges as well, and is not the solution for every challenge out there. So you have to be smart enough to see that if you want to do analytics, first question is it a big data problem? If not, I would suggest to stick with the tools that I mentioned. If it is, focus on the right data. If you have the right data, then use the tools and drive value out of it, and preferably use cloud platform to have rapid time to value and pay as you go and drive value. So that's my key takeaway. If you want to take away mainly these things, if you forget everything, these are the 3 key main points that I will suggest, and it's the crux of this presentation. So that's all from my end. Try to conclude it within the allotted time. If you have any questions, happy to answer.